You probably believe the Union Pacific Big Boy was the absolute pinnacle of steam engineering, the final, untouchable king of the rails that surrendered only to the inevitable efficiency of diesel. The history books tell you it was a clean break, that the 4-8-8-4S were retired, and the internal combustion engine simply took over because there was no other option. But the data suggests a different, far more volatile reality. There was a gap, a violent transition period where engineers refused to let solid fuel die. They built a successor, a machine designed not just to match the Big Boy, but to humiliate it. It was longer, louder, and possessed a power density that frightened the crews assigned to test it. It was officially chosen to carry the torch of the coal-burning empire. But here is what is fascinating. Despite millions in development and a terrifying road test phase, this Leviathan was erased from the roster so quietly that few outside the department even knew the full scope of its failure. Let me show you how the quest for the ultimate locomotive created a mechanical monster that destroyed itself from the inside out. You're watching Rust and Thunder, where iron tells the truth. If you value this depth of forensic engineering analysis, subscribing ensures you don't miss the next investigation into the machine's history tried to bury. To understand the magnitude of this failure, we must first understand the shadow this new machine was forced to live in. The Union Pacific Big Boy was not merely a locomotive. It was a geopolitical statement forged in steel. Delivered in 1941, just as the world was tearing itself apart, the Big Boy was the answer to a specific logistical nightmare: the Wasatch Mountains. Union Pacific needed to drag thousands of tons of freight over a ruling grade that broke lesser engines, and they needed to do it without splitting trains or adding helpers. The result was a machine of staggering dimensions, 132 feet of articulated aggression, weighing over 1 million pounds, capable of generating 7,000 horsepower at the drawbar. It was the apex predator of the steam age. But by the late 1940s, the apex predator was dying. The physics of the Big Boy were undeniable, but the economics were becoming indefensible. The steam locomotive, for all its romantic power, was thermally inefficient. It wasted heat, it wasted water, and it required an army of maintenance crews to keep its firebox fed and its boiler pressurized. The diesel-electric revolution was encroaching from the east, bringing with it the promise of standardized parts, lower labor costs, and higher availability. For most railroads, the choice was simple: scrap the steam fleet and buy General Motors EMD diesels. However, Union Pacific was not like most railroads. They sat on a unique resource that complicated the equation: massive reserves of coal. While the rest of the industry rushed toward petroleum, Union Pacific looked at their Wyoming coal fields and saw virtually free energy. To switch entirely to diesel was to abandon a fuel source they owned in favor of one they had to buy. The executives in Omaha weren't ready to capitulate. They wanted a third option. They wanted the operating range and low maintenance of an electric motor, but they wanted to feed it with the raw, gritty power of coal. They didn't want a better steam engine. The reciprocating piston had reached its limit. You simply couldn't make the cylinders any larger or the boilers any hotter without the steel failing. They needed a propulsion system that abandoned the piston entirely. They looked to the skies, where jet engines were rewriting the laws of thrust. The theory was seductive in its simplicity. Take a gas turbine, essentially a jet engine grounded on rails, and use it to spin a generator. Turbines offered incredible power-to-weight ratios. They didn't hammer the track like the reciprocating mass of a steam engine's driving rods. They were smooth, continuous, and deafeningly powerful. Union Pacific had already flirted with oil-fired turbines, the famous big blows, which sounded like screaming banshees and drank bunker C fuel oil by the tank car. But the dream remained: a turbine that could eat coal. If they could pulverize coal into a fine dust and inject it into a combustion chamber like a fluid, they could combine the cheap fuel of the Big Boy with the futuristic power of the turbine. It was the holy grail of heavy haulage. So, in the smoky backrooms of design bureaus, the specifications were drawn up for a machine that would render the Big Boy obsolete. It would be a 3-unit behemoth. It would carry its own coal processing plant on its back. It would generate horsepower figures that made diesel units look like toys. The engineers were confident. The physics seemed sound on paper. They believed they were building the savior of the coal industry. In reality, they were designing a machine that would subject its own internal components to a torture test no metal on Earth could withstand. They were about to learn that coal does not like to flow like water, and when you force it to, it becomes something far more abrasive. This is the story of Union Pacific number 80, the coal-fired king that never was. The concept required a complete reimagining of what a locomotive could be. It wasn't enough to simply toss coal into a firebox and boil water. That was 19th century thinking. To compete with the sleek efficiency of diesel electrics, Union Pacific and ALCO had to turn solid rock into a gas-like propellant in real time. The result was a machine that looked less like a train and more like a rolling industrial refinery. Designated as Union Pacific number 80, this experimental unit was constructed using the modified shells of older diesel units, but its internal anatomy was unlike anything else on the rails. It was a three-part monstrosity: a lead control unit, a second unit housing the massive gas turbine itself, and a trailing tender carrying the coal. But the real magic and the eventual horror was happening inside the plumbing connecting them. The engineering challenge was staggering. The locomotive had to take nugget-sized coal from the tender, crush it down, and then pulverize it further until it reached the consistency of face powder. This wasn't happening in a stable factory on the ground. It had to happen at 60 miles per hour, vibrating down a track, while pulling thousands of tons of freight. Once pulverized, this coal dust was aerated and injected into the combustion chambers under immense pressure. The theory was that if the particles were small enough, they would burn instantly and completely, just like diesel mist or natural gas. The superheated exhaust would then slam into the turbine blades, spinning the shaft and generating the electricity needed to turn the wheels. On paper, the math was seductive. Union Pacific owned vast coal reserves. If they could make this work, they would bypass the oil industry entirely, running their fleet on cheap, abundant fuel they already owned. It was a strategic masterstroke that would secure their dominance for decades. If you enjoy uncovering these forgotten mechanical leviathans and the ambitious strategies behind them, a like on this video helps us justify digging deeper into the archives. But while the strategists saw dollar signs, the metallurgists saw a nightmare scenario developing in the combustion chamber. The problem wasn't burning the coal. It was what happened immediately after. When coal burns, it leaves behind ash. In a steam locomotive, this ash simply falls through a grate or is blasted out of the smokestack. But in a gas turbine, the exhaust gas, filled with this ash, is the very thing that drives the engine. The engineers knew this. They knew they couldn't just blast abrasive grit directly into the delicate, precision-balanced blades of a turbine spinning at thousands of revolutions per minute. To solve this, they installed an elaborate filtration system known as the Dunlop separator. This device used centrifugal force to spin the exhaust gas, flinging the heavier ash particles to the outer walls where they could be collected and ejected, theoretically leaving only clean, hot air to enter the turbine. They calculated that the separator would remove the vast majority of the larger, damaging particles. And technically, they were right. The separator was efficient, caught the big chunks, but it missed the microscopic silica, the invisible, razor-sharp dust that behaved more like a gas than a solid. The engineers had underestimated the violence of the environment inside the turbine. When a microscopic particle of silica hits a turbine blade that is moving near the speed of sound, it doesn't just bounce off. It acts like a bullet. It gouges the metal. As number 80 began its road tests, the initial reports were promising. The beast produced tremendous power. It roared with a sound distinct from the chugging of steam or the thrum of diesel, a high-pitched, jet engine scream that signaled a new era. It hauled heavy tonnage up the Wasatch grades, proving that a coal turbine could match the tractive effort of the legendary big boys it was meant to replace. The executives were elated. They had built the Holy Grail, a locomotive with the power of a turbine and the fuel costs of a steamer. However, inside the casing of the turbine, a slow, invisible catastrophe was unfolding. The microscopic fly ash that bypassed the separator was sandblasting the turbine blades in real time. This wasn't the sudden failure of a piston rod snapping. It was an insidious erosion. The leading edges of the expensive, heat-resistant alloy blades were being eaten away, micrometer by micrometer. The smooth aerodynamics of the blades, essential for efficiency, were becoming pitted and rough. As the surface grew rougher, the airflow became turbulent, which in turn reduced power and increased the heat, creating a feedback loop of destruction. The crew's operating number 80 began to notice the subtle shifts. The exhaust, which should have been relatively clear if the combustion was perfect, often trailed a distinct, hazy plume. The maintenance teams, upon opening the turbine casing for routine inspections, were greeted not with clean metal, but with components that looked as if they had been attacked by acid. The stator blades, the stationary parts that directed the airflow, were eroding just as fast as the rotors. The solution of the separator had only filtered out the evidence they could see, while letting the true killer pass right through the heart of the machine. Union Pacific was discovering that while you can force coal to flow like a fluid, you cannot strip it of its geological nature. It is rock, and rock is harder than steel. The dream of the coal turbine was effectively a machine designed to consume itself. Yet they didn't stop. They were too deep in the investment, too committed to the promise of cheap fuel to let a little metallurgical erosion derail the project. They ordered modifications. They tweaked the separators. They changed the blade alloys. They were trying to negotiate with physics, convinced that with enough engineering brute force, they could alter the fundamental properties of abrasion. They were wrong, and as the months of testing dragged on, the maintenance costs began to creep up, slowly threatening to eclipse the savings on fuel. The replacement for the big boy was proving to be powerful, yes, but it was also proving to be terminally fragile. To save the project, Union Pacific made a decision that seemed pragmatic on the surface but would ultimately trade one set of catastrophic problems for another. They stopped trying to feed the beast rocks. The coal dust experiment was quietly shelved, the pulverizers dismantled, and the engineers turned their eyes toward a different fuel source, one that flowed, albeit reluctantly. They pivoted to Bunker C heavy fuel oil. On paper, this was the salvation the turbine program needed. Bunker C was the bottom of the barrel, quite literally, the thick, tar-like residue left over after gasoline, kerosene, and diesel had been distilled from crude. It was industrial waste masquerading as fuel, cheap enough to justify the turbine's insatiable thirst. The logic was seductive. If the turbine couldn't handle the abrasive bite of coal particles, surely a liquid, even a viscous one, would pass through the blades without scouring them away. They were trading erosion for combustion, believing they had outsmarted the wear and tear that killed the coal prototype. But chemistry is just as unforgiving as physics. While the coal dust had acted like sandpaper, the Bunker C oil acted like acid. The heavy oil was rich in vanadium and sodium, trace elements that, when superheated in the combustion chamber, turned into a corrosive vapor that attacked the turbine blades at a molecular level. Instead of being sanded down, the blades were being chemically eaten alive, developing a condition known as hot corrosion that left the expensive alloy fins pitted and brittle. Once again, the savings at the fuel pump were being incinerated by the cost of replacing the engine's internal organs. Yet, the Union Pacific refused to blink. They saw raw power where others saw a maintenance nightmare. They doubled down, rolling out the first true fleet of 4,500 horsepower production units. These machines were distinct, sleek, and terrifyingly loud. To the crews who operated them and the towns they passed through, the metallurgical problems were abstract, but the noise was a physical assault. A traditional steam locomotive breathes. A diesel engine throbs. The turbine screamed. It was a high-frequency shriek, comparable to a jet fighter taking off, but one that didn't fly away. It dragged its sonic boom slowly through the canyons of the Wasatch Mountains. They earned the nickname Big Blows, a moniker that commanded both awe and resentment. The sound was so intense it reportedly curdled milk in nearby farmhouses and shattered windows if the throttle was opened too aggressively near a station. In the enclosed cuts and tunnels of the Wyoming Division, the noise reverberated with such violence that it could disorient the crews, vibrating the very fillings in their teeth. If you appreciate digging into these overlooked mechanical realities where engineering meets human endurance, taking a moment to like this video helps support the research required to bring these archives to light. The noise, however, was just the atmospheric soundtrack to a much deeper operational crisis. The switch to Bunker C had introduced a logistical complexity that the big boy never had to contend with. Because the fuel was essentially tar, It solidified at room temperature. Couldn't just be pumped. It had to be cooked. The locomotives required elaborate heating systems in their tenders to keep the black sludge at 200 degrees Fahrenheit, just hot enough to flow into the injectors. If a turbine shut down out on the main line in the dead of winter and the heaters failed, the fuel would harden into asphalt inside the pipes, effectively turning the locomotive into a useless, frozen brick of steel and tar. This created a perverse incentive for the railroad. To avoid the risk of the fuel solidifying, and to avoid the tremendous stress of thermal cycling on the turbine casing, the engines were rarely shut down. They sat in sidings, roaring at idle, guzzling 60 gallons of fuel every hour just to stay warm. It was a level of waste that would be unconscionable in any other era, but in the 1950s, with oil prices rock bottom, up rode it off as the cost of doing business. They were chasing the dream of the superpower locomotive, convinced that if they just built them bigger, the efficiency of scale would finally tip the math in their favor. And so they built the monsters. In the late 1950s, as the first generation showed its age, Union Pacific ordered the ultimate successor, the 8,500 horsepower super turbines. These were not just locomotives, they were rolling power plants, comprising 3 massive units, a control cab, a turbine unit, and a massive fuel tender. They stretched nearly 180 feet long. They were the most powerful locomotives ever placed on a single frame, designed to crush the memory of the big boy by outpulling it at high speeds. When a super turbine latched onto a train, it didn't just start it. It yanked the slack out of a mile-long consist with a violence that snapped couplers and terrified caboose crews. For a brief, shining moment, it looked like they had won. The 8,500 horsepower units dominated the high plains, screaming across the desert at 60 miles per hour with tonnage that would have required 3 or 4 diesel locomotives to move. They were the kings of the main line, the apex predators of the Union Pacific Fleet. They devoured miles and fuel with equal ferocity, embodying the mid-century American ethos that there was no problem that couldn't be solved with more horsepower and more noise. But while the turbines were screaming for attention, a silent revolution was happening on the parallel tracks. The diesel-electric engine, once a weak and complicated novelty, was quietly evolving. General Motors' EMD division wasn't trying to build a single, massive machine to replace the big boy. They were building modular units, the F-units and the early Geeps. These machines were boring. They didn't scream. They didn't melt their own blades. They didn't require preheated fuel. You could shut them off when you weren't using them. And most dangerously for the turbine program, they were becoming reliable. The super turbines were performing a magnificent high-wire act, balancing immense power against fragile complexity. But the ground beneath them was shifting. The cheap byproduct fuel they relied on was finding new markets in the plastics and road paving industries, driving the price up. The specialized maintenance crews required to service the turbines were becoming a luxury. The sheer specificity of the machine was becoming its liability. The big boy had been retired because it was labor-intensive, but its supposed successor was revealing itself to be capital-intensive in ways the accountants hadn't predicted. The turbine was winning the battle for speed, but it was slowly, invisibly, losing the war for economic survival. By the late 1960s, the math had become undeniable, and in the world of heavy freight, mathematics is the only language that matters. The Union Pacific accountants looked at the spreadsheets and saw a grim trajectory. Bunker C fuel, once the waste product that nobody wanted, essentially the sludge at the bottom of the barrel, was suddenly valuable. The petrochemical industry had discovered how to crack it into gasoline and plastics. The road construction industry wanted it for asphalt. The price of the turbine's lifeblood began to creep upward, eroding the single greatest advantage the locomotives possessed. At the same time, the diesel engine was undergoing a renaissance. General Electric and EMD were rolling out second-generation diesels that were turbocharged, efficient, and standardized. They didn't produce 8,500 horsepower in a single unit, but you could lash 3 of them together to match a turbine's pull, and if one broke down, you simply uncoupled it and kept moving. If a super turbine failed, the entire train stopped. The death warrant was signed not with a bang, but with a quiet internal memo. The mighty 8,500 horsepower big blows. The machines that had shaken the ground of Wyoming and terrified livestock across 3 states were to be retired. It was a stunningly fast fall from grace. These machines were the pinnacle of land-based propulsion technology, yet they were being hunted to extinction by boring, reliable, reciprocating piston engines. The Union Pacific began trading them in to General Electric. In a cruel twist of mechanical cannibalism, the turbines weren't even preserved for their engineering brilliance. They were stripped. Their running gear, the span bolsters and traction motors, were salvaged and placed underneath the new GEU-50 diesels. The turbines were quite literally dismembered to build the next generation of conventional locomotives. The jet engines themselves, once the screaming heart of the fleet, were pulled out and scrapped or sold for stationary power generation. The yards in Cheyenne and Council Bluffs, which had vibrated for a decade with the high-frequency whine of aviation technology, went silent. The smell of unburnt kerosene dissipated, replaced once again by the oily soot of standard diesel exhaust. By 1970, the experiment was over. The locomotives that were officially chosen to replace the big boy had been quietly abandoned, pushed onto sidings, and cut apart with torches. It is a sobering reminder of how quickly the cutting edge can become scrap metal. If preserving these forgotten chapters of industrial ambition resonates with you, subscribing ensures we can keep digging through the archives to bring them into the light. Today, the legacy of the Union Pacific tells is one of magnificent failure. Only 2 of these leviathans survive, one in Illinois, another in Utah, sitting cold and silent in museums. They look less like trains and more like grounded spacecraft, their long, smooth fuselages hinting at a speed and power that the rails were never quite ready to handle. Standing next to one, you are struck by the sheer audacity of the concept. It was an era where engineers believed they could brute force their way through efficiency problems, where the solution to moving more freight was simply to strap a jet engine to a frame and melt the snow off the tracks behind it. But the ghost of the turbine program haunts the industry in a different way. It proved that maximum power is not the same as maximum utility. The big boy, the steam giant the turbine was meant to replace, was retired because it was obsolete, yet it remains the most beloved locomotive in history. In 2019, Union Pacific restored a big boy to operation, and millions of people lined the tracks to watch it run. But there will likely never be a restored super turbine. The danger is too high, the noise is too deafening, and the fuel is too specific. They are too wild to be brought back to life. The turbine was a bridge technology, a brilliant, roaring, terrifying bridge that burned bright and burned out fast. It taught the railroad industry that the future didn't belong to the strongest machine, but to the most adaptable one. The diesels that replaced them were unexciting, quieter, and weaker, but they survived. The super turbines, for all their 8,500 horsepower glory, were simply too advanced for their own good. They were the Concorde of the rails, technologically superior, aesthetically distinct, and economically doomed. In the end, the Union Pacific did find a replacement for the big boy, but it wasn't the screaming jet engine they bet on. It was the swarm of efficient diesels that act as the workhorses of today. The turbines remain a buried truth, a time when the railroad tried to fly, realized the ground was safer, and quietly dismantled the wings. The roar is gone, but for those who know where to look, the scorch marks on the history of transportation are still visible.